So antimicrobial resistance is where bacteria pick up a resistance to readily available antibiotics that you can get at the clinic.
Everyone's aware of MRSA, I guess, which is the infection you can get at hospitals, and that's a typical example of a bug that 30 or 40 years ago could easily be treated and now produces chronic infections which can often be fatal.
We need to look at a way of getting around this, and at the moment there hasn't been a new drug created for the last 30 years. So that's where the work that I do comes in. If you get a page of clinically available antibiotics, you'll notice that they all have very similar structures, and I don't use anything like that, so mine are completely new.
We've identified some metal compounds that are potent against gram-positive bacteria, but they're particularly potent against gram-negative ones. One of the ones that we've looked at specifically is an E. coli that causes urinary tract infections, which is effectively almost non-treatable at the moment and causes hundreds of thousands of infections around the world.
I made a series of ruthenium compounds, and we found that the lead one is as active on wild type strains, so wild type's non-pathogenic. It's as active on those strains as clinically available antibiotics, but then it retains that activity in pathogenic multi-drug resistant strains. We think the reason it's so promising as an antibiotic is because it's got two mechanisms of action. So we've got the initial membrane binding, and we see membrane damage, which I've proved by TEM and by an ATP release assay. And then we also see localization at the poles of the cell.
Well, we've identified an entirely new class of compounds that are very active against gram-negative bacteria, and also we can directly image the damage that they're doing with the cells. So those are all new things, really.